Alright, here we go with the Chapter 7 Homework 1 review. The scores on this one were a little bit lower on average. We averaged about a 9 out of 12, where we have been up around 10 out of 12. So I expect the main reason for that is that most of you were too busy preparing for the last exam and not really focused on this assignment. So if there's anything on this homework assignment that you feel like you had trouble with, certainly try to address that as soon as you can. And I'll go over some of the more difficult problems here to hopefully help you get started with zeroing in on some of the things in this one that we need to work on. Okay, so this chapter is all about energy changes and chemical reactions and other physical processes. We look at delta E and delta H, which are two closely related concepts dealing with how energy flows into or out of systems, where the system is often going to be a chemical reaction in our case. So the first concept we have to deal with is sort of the definition of changed energy, delta E. So for delta E, we really have one major equation we have to think about, which is that delta E is equal to Q plus W, where Q is the heat and W is the work. So whenever you're having a change in energy for a system, there's going to be some amount of heat going into or out of that system and some amount of work going into and out of that system that's going to be responsible for the change in energy. And the sum of these two gives you what that change of energy is. Now we're also, as we're going to see in a little bit, we're going to deal with Q and W separately. But in this problem here, we're looking at the combination of heat and work. So we have a system releases 255 calories of heat to the surroundings while delivering 428 calories of work. Calories is just another unit for energy. 1 calorie is 4.184 joules. So basically a calorie is the amount of heat needed to raise 1 gram of water by 1 degree Celsius. But it's related to joules, just about a factor of 4 less. And we have this system releasing 255 calories of heat, delivering to 428 calories of work. What is the change of internal energy? So this change in internal energy is what we call delta E, and it's just going to be the sum of the heat and work. Now the issue here is that we don't always give you the signs directly for heat and work. We have to be able to sort of read the problem and understand the context to know whether Q is negative or positive and whether W is negative or positive. So remember that if we have heat, so we're releasing heat to the surroundings. So if heat is released, or delivered as it's sometimes said, that means we have a negative sign for Q. And then when we have work here, we have delivering 428 calories of work. So if we're doing or delivering work, that's going to be a negative W term as well. Okay, so if heat is absorbed, Q is positive. If heat is released, Q is negative. If work is being delivered or done by the system, that means W is negative. If work is being done on the system, W is positive. So it's important to keep those sign conventions straight, because that's going to be the key to solving this problem, which otherwise is very simple mathematically. So delta E is Q plus W. Both of them are going to go in as negative numbers. So it's going to be, for the Q, it's going to be minus 255 calories. The heat is being released to the surroundings. The system is releasing that much heat. And then the W term is going to be negative 428, because the work is being done by the system. So when we add those two negative numbers together, we get minus 683 calories. Alright, so most of you that got this one incorrectly, you put the wrong sign for either Q or W. I think with the most popular answer, which was C, most of you had the wrong sign for W. So both of these should be negative in this case, based on the sign convention that we talked about in class. So that's kind of how we can combine Q and W together to calculate a delta E. We're also going to have a lot of problems that deal individually with Q and W. So one of the problems that we had a fairly low score on was expansion or compression work. So we have a certain gas compressed in a cylinder by a constant pressure of 9 atmospheres from a volume of 35 liters to 4 liters. Calculate the work for this process. Alright, so this type of problem here, again, the equation is very similar. We have to remember the sign convention, and we have to also think about units a little bit. So the only type of work we're going to actually have to calculate on its own is this, what we call expansion work, which is equal to the negative of the external pressure times the change in volume. Alright, so we're only going to deal with constant external pressures here, and then the delta V is going to be change in volume. So we just really have to plug the numbers in here but then we have to be mindful of the units once we get the number. So we're going to have our external pressure is 9 atmospheres. So 9 atmospheres is the external pressure, and then the change in volume, remember, is V final minus V initial. So the final volume is 4, and the initial volume is 35. So we have 4.00 liters minus 35.0 liters. So that's the calculation we do, but if we're keeping track of our units, we should get 279 liter atmospheres. And this is obviously not a very standard way to report work or energy changes, which are going to be in joules or kilojoules most often. So 279 liter atmospheres, all of our answer choices are in joules, so we have to convert it. So the work in joules is going to be 279 liter atmospheres. And many of you that got this problem wrong picked choice E, which would be without converting it. Remember that this answer here has the units liters times atmosphere. So to convert that, the conversion for that is, I gave this to you in class, 101.3 joules per liter atmosphere. So if you take our answer and multiply it by 101.3, and that gives us then 2.8 times 10 to the 4th joules. So choice A should be the correct one here, and the work term should be positive because we're compressing the gas. So that comes directly out of the equation here. We have this minus sign in front of the P delta V, but even if we didn't realize that, whenever we're compressing a gas, work is positive. Whenever we're expanding a gas, work is negative. Alright, so we have to keep that in mind as well when we're talking about sign convention. Alright, so a lot of you had this one wrong, also had the sign just inverted. That was all you did. Alright, and then finally we have a couple of problems that deal with heat, and specifically these deal with heat transfer between two systems, or between a system and its surroundings, however you want to sort of think about it. So one of them is going to be determining unknown specific heats. So the idea here is that we're taking a 12.3 gram sample of an alloy that's heated up to 93 degrees Celsius, and we're placing it into 52.3 grams of water at 22 Celsius. So the alloy is hotter than the water, so heat is going to transfer from the alloy to the water, and we're assuming that no heat is absorbed by the cup, so all of the heat that comes out of the alloy is going to go into the water. If the final temperature of the system is 31.1 degrees Celsius, what is the specific heat capacity of the alloy in joules per gram K? And we're given the heat capacity of water is 4.184. So in this type of problem, which is a very classic calorimetry type problem, we're talking about heat transfer from a hot object to the water of the calorimeter. So the heat for the alloy is going to be equal in magnitude but opposite in sign for the heat term for the water. Alright, we have to remember that one of these has to have a negative sign in front of it because the heats are going to be, by definition, have opposite signs. Heat is flowing out of the alloy, which would be a negative Q. Heat is flowing into the water, which would be a positive Q. So in order to make them equal to each other, we have to put a negative sign in front of one of them. Okay, but the point is that all of the heat that's left from the alloy goes into the water, so they just set the two equal to each other. And remember, the equation for heat is mc delta T. That's going to be the major equation we're going to use for heat. So we're going to set each of these mc delta T's next equal to each other with a negative sign in front of one of them. So the mass of the alloy times its specific heat times the change in temperature for the alloy equals the negative of the mass of the water, specific heat for water, and the delta T for the water. Alright, and now we just have to start plugging in numbers that are given in the problem. There should only be one unknown, which is the specific heat capacity of the alloy. So the mass of the alloy is 12.3 grams. We have the specific heat capacity of the alloy, which is unknown. And then delta T for the alloy, the final temperature for both the alloy and the water is 31.1 degrees Celsius. That's the temperature at which heat transfer stops. So that's our T final for the alloy. And then the initial temperature for the alloy is given up here at 93 Celsius. And then what we have is, on the other side, we have the same term for water. So we have a negative sign out in front. The mass of water is 52.3 grams. Heat capacity of water is a known quantity, it's 4.184. And then the delta T for the water is the final temperature is still 31.1. And the initial temperature for the water is 22.0. So now we just have to do some algebra to solve for this unknown, the specific heat capacity of the alloy. So the specific heat capacity for the alloy, sorry I didn't work this out ahead of time. Alright, so sorry I need a minute to calculate that. Okay, so the heat capacity we get for the alloy is 2.62 joules per gram Kelvin. Alright, so we just have to set the two heat terms equal to each other, put a negative sign in front of one of them, and solve for whatever our unknown is, which in this case is the heat capacity. Okay, so the next problem is identical in concept, except that we're using two of the same substances. So here we have two iron bolts. One is at 100 degrees Celsius and a mass of 12.7 grams, the other at 56 degrees Celsius with a mass of 15.3 grams, and we place them in an insulated container. Assuming the heat capacity of the container is negligible, which means that no heat is absorbed by the container, what is the final Celsius temperature inside the container? So again, we have two objects placed in contact with each other. One's at a higher temperature, one's at a lower temperature. So heat is going to transfer between the two objects until the temperature is the same and there's no more heat transfer. So the heat for one of them is going to be equal to the negative of the heat for the other. Alright, so Q1 equals minus Q2, or you could also write it as minus Q1 equals Q2. Remember, we just put a negative sign on one side. Alright, so in this case we have, again, for each one, an MC delta T term. So the first mass times its heat capacity times its change in temperature is equal to the negative of the second mass times its heat capacity times its change in temperature. Important point here is that both of these are the same material, iron. So C1 equals C2 equals, and we're given the numbers, 0.450. But if the two substances are the same, we don't even need the heat capacity because we can C1 equals C2, so they can both divide out. So really it's just, we can simplify this and say M1 delta T1 equals minus M2 delta T2. If the two substances are the same, we don't need the heat capacity because it divides out of this equation. Alright, so with that in mind, we can start putting numbers in here. So M1 is the first mass, which is 12.7. In this case, we're solving for the final temperature, so we don't know that, so it's going to be TF minus the initial temperature, which is 100 degrees Celsius. And we're going to set that equal to the negative of the second mass, which is 15.3 grams. And then its final temperature is going to be the same. Remember, the heat transfer occurs until they both have the same temperature. And the initial temperature for the second one is 56.0 degrees Celsius. Alright, so this is the equation we're going to solve. We solve for TF. Again, I'm going to skip a lot of the algebra here, but what we should get for this one is the final temperature is 76.0 degrees Celsius. Okay. Alright, so that's how we're going to do that one. Sorry, I keep getting interrupted. Sorry for the pauses. Alright, so then finally this next question here is sort of a transition into what's going to be one of the major topics in this chapter, which is enthalpy change, delta H. And so this one deals with the relationship between delta E and delta H. So we have a reaction here, and we find delta E is minus 742.7, and we want to calculate delta H for the reaction at this temperature. Now this is a question that will probably make more sense once we go through chapter 8. We gave you all the information here to solve it. It did require a little bit of thought, and we kind of need to know what to do with some of these terms here. Okay, so the relationship between delta E and delta H is other way around. Delta H is going to be delta E plus P delta V. So we're given delta E, we just need this P delta V term here to be able to calculate delta H. However, we're not given anything directly about the pressure and the volume, but we are given this hint here that P delta V equals delta nRT. And that comes from the ideal gas equation, which we just introduced on Friday, and we'll see a lot more of this week in class. So this comes from the ideal gas equation. We can rewrite it as this. And if we look at what's told in the problem, we're calculating it at the same temperature, 298 K, so we don't have temperature changing. R is a constant as well. So R and T are both constants. So what we can really rewrite this as delta E plus RT delta N. Because the other two are constants, the only thing that's changing is the number of moles of gas N. So when we have a delta N term, what that means for a chemical reaction is the difference in the number of moles of gas on the product side versus the number of moles of gas on the reactant side. So delta N is going to be equal to moles of gas on the reactant side minus moles of gas on the product side. Actually, it's the reverse of that, my bad. Just thinking backwards here for a second. It should be products minus reactants. So it's to change the number of moles of gas as the reaction takes place. So it's going to be products minus reactants. Alright, so that's the delta N term. We can calculate it for this one. We have, on the product side, we have 1 mole of N2 and 1 mole of CO2. They both have coefficients of 1 in front of them. And then on the reactant side, the only gas is going to be this O2, and there's 3 halves, or 1.5 moles. So the delta N, to change the number of moles of gas, is 0.5 moles for this reaction. So if we calculate this term separately, RT delta N, it's going to be R, as we've used before, is 0.0821. So we had to look that up, but that wasn't introduced in this chapter. But the temperature is 298 Kelvin, and then delta N is 0.5 moles. So when we calculate that out, we get RT delta N is going to be, let's see what this comes out to. 12.23 liter atmospheres. So again, units are important here. So K and mole cancel out when we multiply, but we're left with liter atmospheres. And then the other hint that we're given here is that 1 liter atmosphere is 101.3 joules. We use that same conversion when doing the work problem earlier. So when we multiply that by 101.3, we get 1239 joules, which is going to be equal to 1.24 kilojoules. So then finally we can add that back in. So our delta H is going to be delta E, which is minus 742.7. That's given to us in the problem. And then our P delta V, or our RT delta N term, which we just calculated here, is 1.24. And that comes out to minus 741.5. Alright, so the correct answer for this is going to be choice C. So as I said in class, and as we can now see with using real numbers, delta H and delta E don't differ from each other by all that much. In this case, it's only by a little over 1 kilojoule, which is very small compared to the size of delta E and delta H for this reaction. But this is how we calculate it. There's a lot going on here. And this hopefully will make more sense once we go through Chapter 8, where now we have this relationship between P delta V and delta nRT, which was given to us in this problem. Alright, so that one, don't worry about it too much because it did skip ahead a little bit from where we are now, but try to understand that, at least the concept behind it, which is the relationship between delta H and delta E. Okay, the rest of these now all deal with delta H's, and we're going to look at 2 different ways of calculating delta H, and then finally one last problem that's dealing with the delta H for a chemical reaction. So here we have very similar one to what we did in class. We want to know the delta H for this reaction, which is calcium plus 1/2 O2 plus CO2 making calcium carbonate. given all this information below. Okay, so remember, this is what we call a Hess's law problem, where we're going to add together two or more chemical reactions and then try to find delta H for an unknown chemical reaction using that. So let's call these reactions 1, 2, and 3, and then try to figure out how to add them together to get our overall chemical reaction. So our overall chemical reaction has 1 calcium as a reactant, and if you look at the given reactions here, reaction 1 has 1 calcium as a reactant. So let's go ahead and use that. Equation 1, by as is, no change. We have calcium plus 1/2 O2. Sorry, that's just those two reactants, and then the product of that first reaction is calcium oxide. Delta H is going to be unmodified, and it's going to be minus 650 kilojoules. Alright, so that's the first step, and then we have to figure out what do we add to that to get our overall reaction. So our overall reaction has CO2 as a reactant and calcium carbonate as a product. So if we take this reaction here, number 2, and we just flip it, that's going to give us calcium carbonate as a reactant and CO2 as a, calcium carbonate as a product, CO2 as a reactant. So if we take the inverse of equation 2, we're going to flip equation 2, that's going to make calcium oxide plus CO2 going to calcium carbonate. The delta H for this reaction is the negative of delta H2 for the second reaction. So remember, when we flip a reaction, we flip the sign of delta H, so this plus 200 becomes a minus 200 kilojoules. Now many of you are probably thinking, oh, I have to use this third one too, what do I do with that one? But if we look at where we are right now, we're already at our overall chemical equation. We don't have to use equation 3 at all. So if we add these two together right now, we see that we get calcium. Let me just leave out the states of matter. I was a little inconsistent with that. So we have calcium plus 1/2 O2. Calcium oxide is our next reactant, but that cancels out with the product in the first reaction. And then we have plus CO2. And the only product that's left is CaCO3. So we can take these first two equations here, by flipping the second one and adding them, we get the overall chemical equation. We don't even have to use equation 3. So that was extra unnecessary information in this problem. And then for our delta H, it's just going to be the sum of these two, minus 650 kilojoules plus minus 200 kilojoules. So we just add the two delta H's when we add the two reactions, and we get minus 850 kilojoules. Okay, so that's going to be choice D in this one. Alright, so many of you that missed this one probably thought you had to use equation 3, but remember, sometimes we like to be cruel and give you information that you don't need, and this was a situation where equation 3 was unnecessary. Alright, so that's Hess's law. And then the next one here, which is a similar type of reaction, decomposing a metal carbonate into a metal oxide and carbon dioxide. Here we're using delta H of formation, which is just a special application of Hess's law. So we're considering the decomposition of this metal carbonate. We're given delta H's for the three species. We have these three numbers here, delta H of formation for the carbonate, the oxide, and CO2 respectively. And then we want to know what's the delta H for this reaction. So if we have a reaction and we have all the delta H's of formation, remember that delta H for the reaction is going to be the sum of the delta H's of formation of the products, so it's products minus reactants, where M is all the coefficients for those products, and we subtract the sum of the delta H's of formation for the reactants. So it's products minus reactants, and in this case what we're going to have is, on the product side we have 1 MO, so we don't have to modify that by any number. So if there were coefficients, we'd have to include them, but there are no coefficients in this reaction. So it's 1 times the delta H of formation for MO plus 1 times the delta H of formation for CO2. That's on the product side, and then we're going to subtract from that 1 times the delta H of formation for MCO3. So now we just put in the real numbers, and we get, for MO, the delta H of formation is minus 525.7. I'm going to be a little bit more careful with units now, since I always preach that. Alright, so we have 1 mole of MO its delta H of formation is minus 525.7 kilojoules per mole. We have 1 mole of CO2, its delta H formation is minus 393.5 kilojoules per mole. And then we're going to subtract from that 1 mole of MCO3, and then its delta H formation is minus 655.2 kilojoules per mole. So when we do all the math, what we get is, just a second here, minus 264 kilojoules. Alright, so this is one of those problems where the numbers were variable, so you could have gotten a different set of numbers here, but it's the same situation anyway. So we have products minus reactants, we have delta H of formation for all of them, so we just add up the two products, subtract the one for the reactant. And we get minus 264 kilojoules in this place. I think I might have picked a weird number here. This should probably be a positive number, but with the numbers that I gave you in this hypothetical problem, this is the correct way to do it, and that is the correct answer based on these numbers. But the decomposition of a metal carbonate should have a positive delta H in most cases, so don't worry about that. Okay, so that's how we do use delta H of formation. The last problem here is what we call a thermochemical equation, and admittedly I did not go over this in class, so if you have trouble with this one, it's probably my fault for not covering this in class. We can go over it now, and we'll see it a little bit more later on. So I talked about hot packs in class. This is a classic exothermic reaction, and if we have a thermochemical equation given to us, 4 iron plus 3 O2 goes to 2 iron oxide with a delta H of minus 1.65 megajoules, and we want to know how much heat can be released if 45.4 grams of iron is consumed. So what we have to realize about these thermochemical equations, a thermochemical equation is a chemical equation with its associated delta H. So when we read this, we can say that when 4 moles of iron reacts with 3 moles of O2, we make 2 moles of iron oxide, and there is minus 1.65 megajoules as delta H, or 1.65 megajoules of heat is released. So anyway, the point is that this number here, minus 1.65 megajoules, that corresponds to the reaction of 4 moles of iron. Here we want to know how much heat is involved when 45.4 grams of iron is consumed. What is the delta H? And it's heat release, so all these are given to us as positive numbers, so we just have to calculate the magnitude and then pick the number that's correct. So when we do this, we're looking for the absolute value of delta H, the heat released, and we can just basically treat this like a stoichiometry problem. So we have 45.4 grams of iron. We can convert that into moles using the atomic mass of iron. So 1 mole of iron is 55.85 grams. Alright, so that gets us into moles of iron, and then finally we use the thermochemical equation to convert moles into amount of heat. So we have 1.65 megajoules for every 4 moles of iron, because there's a coefficient of 4 in front of iron. So we're just using that delta H as a conversion factor now. And then finally, all the answers are in kilojoules. So megajoules is 10 to the 6th joules, which is equal to 10 to the 3rd kilojoules. Alright, so there's going to be 1 times 10 to the 3rd kilojoules in 1 megajoule. Alright, so remember that. We have to remember these prefixes. Mega means 10 to the 6th. So when we multiply this out and get it into the correct units, we get 1.34 times 10 to the 3rd kilojoules, which corresponds to choice A. Okay, so thermochemical equation is really just an extension of stoichiometry. We have a delta H that's associated with a chemical reaction, and that tells us that that much heat is either absorbed or released for this many moles of substances. So we interpret the coefficients as moles, and in this case the key conversion factor was this one, 1.65 megajoules of heat released for every 4 moles of iron that react. Alright, that takes us to the end of what I wanted to talk about today. Any additional questions on this homework assignment, please come to me to talk about them, and I will see you in class later today.